Welcome everyone to today's webinar. The speaker for today's webinar is John Handler. He's the Principal Solution Architect with AWS. Let me hand over the control to John. Over to you, John.
Good morning, everybody. Thanks for coming out this morning. Appreciate your time and attention. My name is John Handler. I'm Principal Solutions Architect with Amazon Web Services, and I work with our search services, principally Elasticsearch service, but also with Amazon Cloud Search. And this morning, we are going to be focusing on Amazon Elasticsearch service for the webinar. So I usually like to start my presentations by asking for a show of hands for who has anything that produces logs. And of course, everybody has things that produce logs because we all have applications, we have servers, we have mobile applications, we have web applications, we do metering, we have IoT. All of these things produce data in the form of logs, among other things. And the problem is, if I take one of those logs and it is a text file, now I could actually read all of this. So this is an example here on the screen of an Apache weblog. And this Apache weblog is showing, all of the access to my web server. If the phone goes off at 3 in the morning and I have to figure out what's going on with the website because I'm having a problem, and if I have thousands of servers and terabytes of data, there's no way that I can look at that in this format and figure out what's going on. And similarly, for all of the data that we produce, that actually machines produce, we have all of this data, but we don't have an easy way to get at it in a text format. Now, we have a tool, though, called Elasticsearch, which allows us to flow that log data into Elasticsearch, which is a search engine, and Elasticsearch holds it and then provides a UI called Kibana that allows us to visualize the data that's actually in our log files in a useful way. So, for instance, I can get some metrics like counts, unique counts of people who are hitting my website. I can look at different places that are generating that traffic, etc. So Elasticsearch is a technology. Again, Elasticsearch is a search engine in much the same way that you would use Google to search over web pages. You use Elasticsearch to search over data that you have put into the search engine. Elasticsearch came out in about 2009 and initially as a full-text distributed search engine that allowed people to search through their text documents and provided, normal search-like experience. Then a technology called Logstash came along. Logstash is a streaming ETL over streaming data that allows you to transform data as it comes through the pipeline and deliver that data principally to Elasticsearch. Kibana, again, web UI that allows you to visualize the data that's in your logs. So the three of those became paired together and called the ELK stack, and this allowed people to start flowing their log data in and start visualizing it and making it more useful. Now the issue with the ELK stack is it's tremendously easy to get started. It's very easy to spin up a search cluster, an Elasticsearch cluster, very easy to flow data in there with Logstash. But as you try to grow and as the data size grows, as the amount of logs that you have grows, ELK can be very difficult to scale. And we find this across the board from people that we talk to, that managing ELK is difficult. So in 2015, we came out with Amazon Elasticsearch service that provides a managed experience that makes it easier to deploy and operate Elasticsearch in the AWS cloud. We primarily wanted to make sure that it was easy to use Elasticsearch and that we added a few features and benefits that make it a great experience to run Elasticsearch on AWS. The first of those is we provide easy APIs to create Elasticsearch clusters. So with a single API call, you can have a cluster deployed and ready for use in a matter of minutes. Second of all, we wanted to make sure that we provided an open source experience. So Amazon Elasticsearch Service provides you direct access to the Elasticsearch API and supports the ELK stack so that you can use an Elasticsearch Service version of Elasticsearch as a drop-in replacement for an existing Elasticsearch cluster that you have. Some of the features that we added security in the form of AWS Identity and Access Management, or IAM. You secure your Elasticsearch clusters with an IAM policy that allows you to control who has access to read and write from that cluster and down to an index level of granularity. We have a feature that makes Elasticsearch Service clusters highly available. With our zone awareness feature, you can split your cluster into 2 different AWS availability zones, and this gives you replication of data across those zones. We provide a number of integrations with other AWS services to make it easier to get data into your Elasticsearch Service domain. In particular, we integrate with Amazon Kinesis Firehose, IoT, and CloudWatch logs at a console level to make it very simple to get your data into the service. Finally, we make the service easily scalable. So we have an API that allows you to deploy a cluster. Additionally, we have an API that allows you to change a cluster configuration. If you're running a particular set of instance types and you want to change to different instance types, you can do this with a single call. We seamlessly bring in new instances in the back end and cut the data across between the 2 sets of instances, and you're then on the new configuration. Again, seamlessly while it runs and you have full access. We see 2 main use cases where Elasticsearch service is used. The first of those falls under the rubric of log analytics. Now this is more broadly any kind of streaming data that you would send into Elasticsearch service. What we see customers doing here, we see many customers who are monitoring their infrastructure simply to use Kibana to visualize server uptime, server loads, problems that are going on in terms of the error codes they're receiving, etc. As we get higher up in the abstraction layer, we talk about application logs. We'll go into a couple of examples in a second, but customers do various things to make sure that their applications are functioning right, and indeed to even get analytical kind of information as their users interact with their software. The second use case is a full text search use case, and again, Elasticsearch is a full text search engine that provides you the ability to match free text as well as to perform structured and other kinds of expression-based searching with adjustable relevance, faceting, filtering, etc. So it's a full text search engine. We do see maybe 30–40% of our customers using Elasticsearch service for full text search. Some of our customers that are using Elasticsearch service at various levels of scale. The point I like to make about this slide is, yes, we have a broad range of customers across many different verticals, and this really speaks to Elasticsearch's popularity and use as a monitoring tool. You know, in all of these cases, we see these companies using Elasticsearch to monitor their infrastructure and do the kind of log analytics that I was talking about. A couple of examples. First of all, we have the Adobe Developer Platform. They are taking logs from their API servers. So as their customers are interacting with the Adobe API servers, they're shipping all of those logs. Now they're a very high volume use case, so they're using Amazon Kinesis Streams to handle the influx of data from all of those servers. They then pass it through Spark streaming, and they do a little bit of a modification on the data. They roll it up into 1-minute windows to make it, somewhat lower volume before sending it off to Elasticsearch service. They found this was a really effective solution for them. They're sending over 200,000 API calls per second at peak, and all of that data is going to Elasticsearch service. As they were doing the development, they really had a nice benefit of being able to switch around their deployment and instance types, and they were able to take advantage of that to make sure that they dialed in their deployment exactly to the resource needs that they had. A second example of streaming data is McGraw-Hill Education. McGraw-Hill Education is an online learning software. They have a catalog of classes. Students sign up for those classes and teachers deliver them. They wanted to use Elasticsearch to analyze the performance of not only their software, but also of the students and teachers who are using that software. So they flow in all of the data as students and teachers interact with their website into Elasticsearch service. And then they don't use Kibana, they use actually Elasticsearch query language to send queries and figure out things like what was the class average and how engaged was this teacher with their students, and how much did the students learn in this class versus that class. So they had a real analytics kind of solution and problem. And for them, the scalability of Elasticsearch service was really a big benefit. They start the school year with no data whatsoever. And as it goes on across the 9 months of the school year, they grow out to be 32 terabytes of data. With Elasticsearch service, they were able to deploy they were able to use a small deployment to start out with and then grow that deployment as their data grew along with it. So we'll talk a little bit about Elasticsearch service now and walk through some of the basics of how to think about deploying a cluster of Elasticsearch and what does that mean and how does it operate. When you use Elasticsearch service, you create what we call a domain. An Elasticsearch service domain wraps all of the software and hardware that is used to run Elasticsearch in the AWS cloud, along with the additional security and monitoring and other features that we provide with the service. So domain is just a group name. You use the SDK, the CLI, the console, CloudFormation to deploy an Elasticsearch service cluster. And again, Elasticsearch is a clustered technology. So we have a collection of nodes. First, we have data nodes. The data nodes hold the data and respond to queries and updates. Then we have master nodes. Master nodes are orchestrators. They manage the data nodes. All of those nodes exist in a cluster, and all of them perform the tasks of Elasticsearch together. In front of the cluster, we put elastic load balancing, just to spread the load across the nodes in the cluster. In front of that, we have identity and access management, AWS IAM, to provide security for the cluster. And then we send monitoring information to CloudTrail and to CloudWatch so that you can monitor the performance of your cluster and make sure that everything is going well. When you're creating a domain, the first thing that you have to think about is how many instances do I need to have in that domain to support my problem? So there's a little bit of a kind of joint question here, and at a very simple level, we can take this as a question of storage. So I want to look at the number of instances and I want to look at the storage type to figure out how many instances I need to support my workload. But before we can talk about that, we have to go a little bit into how is it that Elasticsearch stores data and how is that data organized within the cluster. For log analytics use cases, we typically see customers streaming across a number of different indexes. Essentially, this is a write once scenario. So customers will create an index for each day, and many of the tools already do this automatically for you. That index consists of the set of all of the documents that are in that search index. Indexes are divided into shards. Each shard is a subset of all of the documents that are in the index, and shards are non-overlapping, they're all distinct. Indexes can have one to many shards. The shards contain documents. The documents themselves are not what we think of as a kind of Office document. They're not Word documents or PDFs or whatever. For log analytics, each log line corresponds to a single search document. Documents are what you put into a search engine. Documents are what you get out of the search engine. The document is composed of a set of fields and values. So if we think about Apache weblogs, we have a host, we have an ident and an auth field, we have a timestamp, we have a request, a verb that was given with that request as well. So this is the logical structure of the data within Elasticsearch. Elasticsearch is partly called Elasticsearch because it takes that data and it deploys it elastically onto a cluster of instances. So in this case, and how it does that is it deploys the shards themselves. The shards are the storage and computational pieces of Elasticsearch. In fact, they're an instance of something called Apache Lucene, which is a Java library that provides reading and writing of search indexes. So each shard holding some set of documents is deployed onto a particular instance in an Amazon Elasticsearch service cluster. In this example, we have 2 indexes, and each of them has 3 shards. Shards come in 2 flavors. There's a primary shard, that's the first shard for each one. In addition, you have a set of replica shards, which you can dynamically set from 1 to n. In this example, we have a single primary shard and a single replica shard for each of our shards. You'll notice that those are then deployed onto the instances in the cluster in such a way that no primary or replica sits on the same instance. This gives Elasticsearch some resiliency to individual instance failure. If an instance goes out, I still retain one copy of that data somewhere else in the cluster. If I bring in a new instance, Elasticsearch is able to then recreate that set of data on the new instance and recover from that failure. So if we think about how many instances we want, again, we have a number of shards that are deployed roughly evenly onto a set of instances. Well, again, we can look at it as a sizing problem, or from the size perspective. So we'll say, let's say we have a 2 terabyte corpus. Now, when I send in 2 terabytes of log lines, Elasticsearch creates an index out of those log lines, which is not exactly the same size as the source data was. In fact, it ranges from smaller than to larger than the source data. But in typical cases, the index size is about the same as the source corpus of documents, usually 1 to 1.1. For each replica that we deploy, we have to add an additional set of storage, right? So if I start with my 2 terabyte corpus and I end up with a 2 terabyte index, and then I add a replica, I'll need 4 terabytes of storage to store that index. We can then size based on storage requirements. We can use local storage or EBS storage, and for EBS storage we can get as large as 1.5 terabytes per instance. Taking all of that, we can simply divide. We can say, okay, I have a 2 terabyte corpus with my replica, that's 4 terabytes of index I need to store, so that will require 4 instances. If I have a 1.5 terabytes per instance, it gives us 6 terabytes total of storage. We divide that, we have a little overhead in there, that's good because again the index will be a little bit larger. So this is the right sizing for this 2 terabyte corpus. When you create your Elasticsearch index, you set the number of primary shards. It's very important to get the number of primary shards correct so that they're not too big and they're not too small. There's a lot of information out there about how to size shards, but again, at a very simple level, we can take this as a problem of storage. So as a best practice, set the primary shard count so that the shards are less than 50 gigabytes. To do this, you can divide your index size by about 40 gigabytes. You can shade it up or down to get an initial shard count. So if we look at our example here again, 2 terabyte corpus will need 50 shards. Taking 2,000 gigabytes, dividing by 40 gigabytes per shard, we should use about 50 shards for that. And we use 40 gigabytes as a target because that gives a little overhead as your indexes roll forward day to day. You won't have to adjust anything quite as often. Then comes the tricky bit, because we've so far sized based only on storage. The next thing we have to do is adjust for workload. There are some general rules here, but mostly what you do is you try it out, run your workload against it, and see how it comes out, whether you're over or underscaled. Just 2 little tips. The more shards you have, you end up parallelizing your writes better. So for higher write capacity, and this is usually the case with log analytics, for higher write capacity, you want to shade up in the shard count. Now, the more shards you have, though, the more your query gets distributed and the more individual shards have to respond for queries. So for queries, you tend to want fewer shards. Generally, again, log analytics, we're dealing with writes, not reads. So generally for log analytics, you want more shards. For query or full text use cases, that's where you'd see perhaps you'd need fewer shards. Then as we're sizing it out, we also want to look at how many shards are going to be active on each of the instances. And as a general guideline, the active shards per instance should roughly be the same as the number of CPUs on that instance. So if I'm thinking about, and when I say active shards, what I mean is Elasticsearch for log analytics is a write-only kind of use case. So I'm writing to one index at a time. And all of the other indexes are there and they're responding to some queries, but mostly what I'm doing is writing. So in that case, I can essentially ignore the old indexes and just look at it as a single index and say, okay, if this index is spread across all the instances in my cluster, how many shards would I have per instance? That should roughly equal the CPUs that you have on the instance type that you select. Last point, always use at least one replica for production use cases. As we saw in the previous slide, the first replica provides you a second copy of your data within your cluster. So one replica provides you with redundancy and the resiliency in the case of a single instance failing. Further replicas are usually used to add additional query capacity. So for full text search use cases, you sometimes see multiple replicas spread evenly across additional instances. But the point I want to make here, you should use one replica for all production use cases. So let's talk a little bit about instance type and how do you pick an instance type for your Elasticsearch use case. You can see here on our console you have the choice to choose among the supported instance types. And the instance types that we support are the T class, the M class, the R class, the C class, and the I class. For the T class of instances, these are really an entry point. They're really only good for dev and test. They're not for production use cases, so put those aside. The M class instances have a balance between the CPU and the RAM that they provide. And so they're a good starting point for almost all use cases. They're, again, very balanced and are good in those cases. The R class instances have additional RAM, which helps Elasticsearch in queries especially, but also helps for writes. So we see heavier workloads or read-heavy workloads migrating to the R class of instances when the M class kind of runs out for them. The C class of instances with more CPUs supports more concurrency. So if you have a very high connectivity that you're trying to support, you'd want to head towards the C class. And then finally, the I class of instances with 1.6 terabytes of SSD local storage has the largest attached disks of any instance type that we support. we do find that the instance storage is slightly quicker than the EBS storage. In most situations, it doesn't matter, especially for log analytics. We do recommend EBS volumes, and we do recommend the GP2 general purpose EBS volumes as the right choice. However, instance storage will give you up to a 10 to 15% performance improvement, which usually matters for, again, full text workloads, not so much for log analytics workloads. When we think about instance sizing, and I just wanted to give some example or some feel for what are the instance sizes that would be appropriate for different workloads. Starting out at the small end, we do see a lot of customers who have application instances with Logstash or the newer Beats co-located on the application instance, tailing the log lines and sending those to Elasticsearch directly. In this case, we have the M4 class. M4 large is our entry point default instance type, up to 200 gigabytes a day with 100 gigabyte EBS volumes or larger, depending on how much data you're storing, is a good choice. We do also recommend master nodes. We'll get to those in a second. For larger use cases, a couple of points to make. When you have a large set of instances and you outgrow the number of CPUs that you can support with connectivity, then you need some kind of buffering solution. In this case, we recommend Amazon Kinesis Firehose to take your data, transform, and deliver it to Elasticsearch service. And here we're seeing up to a terabyte of data a day, something like on the R4, 2x larges with 1 terabyte volumes, and again, 3 M4 large master nodes is the recommendation. Finally, at the high end, and again, this is thinking about the Adobe use case, what we see is we have many, many data producers, and we need some really large-scale way of handling all of that data. Well, many customers use Amazon Kinesis Streams, or they use Spark along with that, or they use EMR. And this is, again, 1 terabyte plus per day. We're then looking at kind of getting into the larger instance sizes like the 8x large for the R4s. As the number of data instances grows, the number of master nodes is going to grow in size and complexity. C4 2x large for an XL use case is a good place to start for this. I want to touch on a couple of the features that we have that we provide through Amazon Elasticsearch service. The first of those is dedicated masters. You'll see in our console you can choose to enable dedicated masters. If you click the checkbox, you'll have a drop-down that lets you set an instance type and an instance count for the dedicated master nodes. So what are dedicated masters, and should you use them? Well, every Elasticsearch cluster has a master instance. That master instance is responsible to know what are the indexes, what are the schemas for those indexes, what are the shards, where are the shards located, which are the nodes in the cluster, and where are they. So essentially, it's keeping track of cluster state. So the problem is, if I have my master instance, which is tracking my cluster state, co-located and doing the same functions as the data instance, which is reading, which is handling updates and responding to queries, then my query or update volume can actually overload that node, and all of a sudden my coordinator goes away and my cluster dissolves. So it's not a great idea to keep the master function on the same instance as the data instances. When I employ dedicated masters, what I do is I take that master function and I push it onto a node that's not a data node. So dedicated master nodes are nodes that do nothing but provide the master function, or provide a way to do the master function. Now, the master instance in a cluster is elected based on a majority of the instances that are eligible to be masters. So if I have an even number of instances eligible, then, and I have a split, a network split, then each half could get enough to elect a master. In that case, my cluster will turn into 2 clusters, and that's not a good thing. So an even number of dedicated masters is not a good thing. You always want to use an odd number of dedicated masters. And one dedicated master is really not enough. If that master goes away, again, you don't have a backup. So you want to use 3 dedicated masters in all cases where you want to use masters, at least 5 or 7, perhaps in very large clusters. We recommend that you use 3 dedicated masters for all production workloads. In some cases, if it's dev and test, you don't care so much. If your cluster goes away, you can rebuild it easily. But in production, we recommend that you use 3 dedicated master nodes. And in terms of the master nodes themselves, they're doing a lot less than what the data nodes are doing. So you can use much smaller instance types, and you can use, again, only 3 of them to manage really large clusters. So if we look at the number of data nodes that are in your cluster, we can recommend master instances based on that. For up to 10, the M3 medium is the lowest cost option for master nodes. Up to 20, we'd like to see you go to a large instance type. 50, we'd like an extra large, and up to 100, we'd like a 2x large. Again, we've chosen M3, M4, and C4. Your mileage may vary, and with all things scale for Elasticsearch, it depends on testing. So try it out, but these are a good place to start. The next feature I want to talk about is zone awareness. So with zone awareness, again, we split the instances in the cluster into 2 different availability zones. And then we make sure that the primary and replica shards are separated into different zones. In this way, you have redundancy where 100% of your data resides in each of the availability zones. If one zone should become unavailable, you retain 100% of data online, so you haven't lost any data out of the cluster. We do recommend zone awareness, again, for production use cases where the data itself is important to maintain online. It's important to add that high availability. In terms of the cost of Elasticsearch service, we charge based on 3 dimensions, 2 of them primarily. With Elasticsearch service, you pay for the instances in the cluster. You pay hourly. And then if you choose EBS as your storage option, then you also pay for the EBS volumes. The 3rd dimension we also charge is AWS data transfer. This is the standard data transfer charge that you would incur across AWS. We do qualify for free tier. So if you are free tier qualifying, you can use a single T2 small to try out the service, see how it goes, get a feel for it, and use it for free. So I just want to sum up. That was a lot of information on scaling and features of the service. So some of the things we covered, the data nodes you should size initially based on the storage. So you take the storage needed, divide by the storage per node. That tells you how many data nodes you need. We do recommend, again, the GP2 EBS volumes for the log analytics use case, 3 dedicated master nodes for production, and zone awareness. The last one we didn't cover, I'm going to skip it. So once we understand how to deploy an Elasticsearch service cluster and how it operates, the next question that comes fairly urgently is, well, how do I get data into it? So we have a number of different ways of getting data into Elasticsearch, corresponding to a number of different technologies that you might use. We have on the left a set of data producers. Those are generating log data, streaming data, all of that. We would send that, again, through Kinesis Firehose will be our recommendation. We'll go into depth on that. CloudWatch Logs, if you're already sending log data to CloudWatch Logs, it's very easy to forward that data to Elasticsearch service. You can do it in the console. It's just a few clicks. You send it off to Elasticsearch, and then you can use Kibana on top of that. For IoT, again, IoT can integrate directly with Elasticsearch. So if you're sending data through IoT, you can get it to Elasticsearch. And again, if you're using Logstash, that's another way to get data into Elasticsearch. Lambda is kind of the all-purpose tool across AWS, and it's true as well for Elasticsearch service. With Lambda, you can take records and transform them and send them into Elasticsearch service. Some of the use cases that we see, if we have a data lake kind of scenario where we're sending a number of files into a data lake somewhere, you can trigger a Lambda function on the S3 create event, pull the metadata for that object that landed in S3, and then push that into Elasticsearch to make Elasticsearch your catalog for searching what's in your data lake. You could also pull the data out of the object itself and use that and send it to Elasticsearch. Some customers are sending their log data in bulk blocks into S3, then reading that out of S3 with their Lambda and pushing it into Elasticsearch service. Similarly, if I'm using Amazon DynamoDB and I'm sending data to a table, I can trigger a Lambda function off the Dynamo stream and push that data into Elasticsearch. And then finally, Amazon Kinesis Streams provides the ability to trigger Lambda on events. So if I'm streaming data through Kinesis Streams, I can easily move that data into Elasticsearch via a Lambda function. I'm going to talk a little bit in depth about Kinesis Firehose because I think it's a really nice method for getting data into Elasticsearch. Firehose provides a delivery stream, which is the underlying mechanism. It can send to S3, Redshift, and Elasticsearch service, and it provides a simple HTTP REST endpoint where you simply push records into the stream to deliver it to your destination. Firehose has a number of features that make it a really nice delivery architecture. So we have our data sources. They're pushing source records into the delivery stream, which, by the way, also can happen with the Kinesis agent that can tail your log files and push those into Firehose as well. Firehose then will call out to a Lambda to allow you to transform that data while it's in flight. So Firehose delivers batches of data to Lambda. You can transform that data in Lambda and send it back to Firehose, and Firehose will then deliver that data to Elasticsearch service. Firehose handles failures and retries in a really elegant way. As you're sending data in, you can set a buffer size so that you're buffering your data and sending it in bulk to Elasticsearch. It deals with delivery failures, so if records are not delivered correctly, they're pushed off to S3. It deals with retry, so you can set a window that says retry my batches for up to this amount of time, and you don't have to worry about writing that in Lambda or dead letter queues or anything else. Firehose does all of that for you. In addition, Firehose can send all of your source records to S3. So this is a nice way to maintain a backup set of your log data in S3 and also send that data simultaneously to Elasticsearch. And just to make the point, what are you doing in terms of the transformation? Elasticsearch works with structured JSON. So what you send into Elasticsearch is not what we have at the top here, which is the original Apache weblog line. In fact, you have to transform that into JSON as below here. So I have the verb, the ident, the bytes, timestamp request, etc. All of that is field and value pairs. Those fields provide the basis for Elasticsearch to search with, and also these are the things that you can visualize with Kibana. So documents, again, contain these field value pairs. Fields can be nested, so you can have a field within a field, and Elasticsearch natively handles that nested JSON, providing you .path access to the eventual values. There are all kinds of different value types, including text, dates, geo-objects, and more. Values can be single or array, so you can send in a single value as I'm doing here, or I can send in an array of values if I have multiples for a particular field. Elasticsearch, again, should receive JSON. Within Firehose, we do provide Lambda blueprints for some common use cases. So in particular, if you're sending Apache weblogs to Elasticsearch service, if you send them via Firehose, we have an Apache log to JSON transform. You can simply click and use that one within Firehose to automatically transform your data into that JSON. We also have a syslog to JSON format that works with Elasticsearch service. So again, some of the features that Firehose has that make it great for ingest. Serverless scale, didn't mention it, but with Kinesis, it's serverless, it scales automatically, and it provides you with almost limitless capacity to scale out. The error handling is great, the retries, the buffering windows, and then the S3 bucket where your failures land up provide you a means of going back and looking at that data that failed and retrying it. We didn't cover any of these best practices. I'm going to skip over these. Actually, I'll just say a couple of things. With Firehose, again, you set a buffer, and that's based on the amount of time you want to wait and also the size of data that's going through. So use smaller buffer sizes to increase your throughput and decrease your latency to searchability, but you have to be a little bit careful that you don't overwhelm your cluster with too many write requests. Firehose does rotate your index for you. You can choose daily, weekly, monthly, or hourly, and daily is correct for most use cases, out to about 1 terabyte. Hourly would be multiple terabytes per day, and larger than that, weekly, monthly, you could use for 250 gigabytes to 100 gigabytes to 1 terabyte over that time period. So I'm going to talk a little bit about Kibana and what Kibana does and how Elasticsearch supports log analysis. And the feature that Elasticsearch has is called aggregations. So if we look at an aggregation, what an aggregation does is it takes the values for a particular field and splits them into buckets and then counts or does other math on the contents of those buckets. So here's an example. If I have an Apache weblog and I want to look at all the traffic from a particular host with and figure out what are the verbs that HTTP verbs that host is sending, I look up, Elasticsearch looks up in its index that host name. It finds there the list of all of the documents that contained that host name. In other words, this is a straight up list of all of the weblog lines that came from that host. It then looks at the verb field and gets the data that is attached to each of those documents. In this case, we have a couple of gets, a post, another get, put, etc. It creates buckets out of the different values of that field data, and then it simply counts how many times did each of those values occur. So aggregations then generalize this concept of buckets and metrics. So a bucket is some collection of documents meeting some criterion, and a metric is a calculation on the contents of that bucket. So in particular, a very common aggregation is to go across the x-axis and bucket by time, and then count how many objects fell within that time window. This is a graph, for instance, of all of the traffic into my website. So I can take all of my weblog lines, I can put them into buckets based on their timestamp, and then I can count how many objects fall in each of those buckets to provide me a histogram of the traffic over time. But aggregations get much more complicated than that. I can take buckets and sub-bucket. So this is a pie chart of some of my CloudTrail logs. I'm looking at the ARN of the sender of those requests, and then I'm bucketing within that by the region that request was issued in, and then I'm further bucketing by the event name or what what was called, and then I'm counting. So I can see I have a major caller over here. I have a smaller caller, my regions break down, etc. I can use this to track what's happening in real time. Some of the other things that you can do with Kibana, we have metrics that, again, allow me to just count things. So here's for weblog lines, this is the total events in the time period I'm looking at. This is the requests I've received. This is the different hosts, the unique hosts that have sent me those requests. I can have line charts. This is a line chart that's graphing the size of the data that I'm sending out. So I'm bucketing again by time on the bottom, and then at the top I'm looking at how much data is flowing out of my website. I can break it out in more complicated ways by looking at different hosts and how many requests those are sending. I can again get a pie chart. Again, this is host and request. And I can even have a heat map that lets me find hotspots in my requests of data. This is again looking at the URLs that I'm receiving for my weblog and finding where I have the hotspots during different times of day or different days. And then finally, I can visualize some stacked bars if I want to look at totals and the breakdown of items within the totals. So the takeaways in terms of Kibana are that Elasticsearch itself works on statistical data, looking at counts and sums and mins and maxes, averages across buckets that are defined by a query. The visualizations themselves are buckets and metrics, and frequently you want to use a histogram of time on the x-axis and then sub-aggregate to get your y-axis. So in summary, Elasticsearch Service provides you an easy way to run Elasticsearch in the AWS cloud. Firehose is a great tool for ingesting data, and with Kibana, you can monitor your infrastructure in real time, dig in and find problems, and make sure everything's running well. So thank you very much. I am going to switch over to the questions now. All right. Okay, so one question, is Elasticsearch only for searching log files? So as we talked about, there are two main use cases for Elasticsearch Service. The first of those is logs, but also streaming data, web application data, as we heard about with McGraw-Hill, etc. The second use case is full text use case. We do see a number of different customers who are using Elasticsearch Service to support their web applications for things like e-commerce and application search across whatever the data the application is providing as well. So here, there's a longish question. We're using a Spring Boot Java application, and essentially the log lines in the Java errors are multi-line. And so how should we handle that? There are a couple of different ways. If you happen to be using Logstash, Logstash does have a way of condensing multiple lines into a single line. I don't remember the syntax off the top of my head, but one of the filters does allow you to condense multiple lines into single lines. If you're not using Logstash, if you're using something like Firehose or otherwise using Lambda, that's the place where you really have to do that data transformation to take those multiple lines and condense them into a single line so that they go into Elasticsearch as a single document. An alternate that you could do is you could send them as a multi-valued field so that each line was part of a message field or some multi-line field that you were using to search within Elasticsearch. So here's a question. What's the difference between CloudTrail and Elasticsearch service? CloudTrail is a service that receives logs from other AWS services. So when I interact with the EC2 console or the S3 console, or I send data, or I create a Kinesis stream, those AWS services, EC2, S3, Kinesis, send logs to CloudTrail. CloudTrail provides you some basic capabilities to search and display your log lines. Similarly, CloudWatch Logs does provide you with some basic capabilities for searching and displaying your log lines. The difference is that Elasticsearch service, number one, is real-time. So with Elasticsearch service, I'm sending my logs in real time, and I'm able to visualize in real time what's happening right now. And second of all, Elasticsearch has a much broader capability to provide you with the ability to search your data. So CloudTrail, CloudWatch Logs, they're not fundamentally search engines. Search engines are good at natural language. They know how to decompose and make things searchable easily. Okay, is it compulsory to use Lambda to push data from CloudWatch to Elasticsearch? Can't we directly send data from CloudWatch to Elasticsearch? CloudWatch provides the integration via Lambda, and other than triggering off a CloudWatch event, there's really no way to send data directly from CloudWatch to Elasticsearch service without having Lambda involved in some way, shape, or form. You could use Lambda to send to Kinesis, Kinesis Streams, or Kinesis Firehose from out of CloudWatch, but there's no direct way to get that data across. Sorry, I'm just scrolling down the questions here. I'm trying to get to them all. So can it handle logs from mainframe systems as well? Do you have any examples? I don't have any examples of mainframe systems sending logs. And the real question to me would be how to get those logs off of that mainframe. If you're able to stream that data into the cloud in some way, shape, or form, generally S3 I would think would be the right destination. And then using Lambda to transfer from S3, potentially translate into Lambda and send off to Elasticsearch service. I think the real question is how to get that data into AWS, and I'm not sure of the answer. It's obviously going to depend on the mainframe and your means of connecting to AWS. How can we use media files with Elasticsearch for streaming? So Elasticsearch, well, one thing to say, Elasticsearch is not actually streaming any files. So generally with media, what we would see is that Elasticsearch would provide you with a catalog of the media files that you have, and potentially, if you're building an application that is taking media in and providing the ability for customers to find that media and to watch it, Elasticsearch would play a role as the catalog that would support customers searching the different media that you have for them to find and watch it. So does Elasticsearch provide CloudWatch metrics and similar dashboards like Kibana? So Elasticsearch does support, getting metrics out of your log data. It's not, so we do also provide metrics to CloudWatch. So your Elasticsearch service domain, we publish about 20 metrics that cover things like the JVM memory pressure for your Java JVM, the CPU utilization on your instances, the free storage space in your cluster. We have a host of EBS metrics that we publish around the read and write latencies, queue depths, other things like that. So please explain, what is full text search? So full text search is what an example of full text search is Google. So what Google does is Google goes and it takes web pages and it indexes them in a search engine. A web page is a search document in Google. And with Google, you get a box where you can type a few words. Then Google, the search engine, takes those words, matches them against text that it's found on the web pages to retrieve for you matches for the text that you've typed. Now, there's a language processing component of that. There's a search component of that. Google, is matching your words to the words it finds, and there's a relevance component of that. It doesn't retrieve everything for you. It retrieves the best matches for what you've typed. And all of those are sort of core components of what we think of as full text search. Is it like a BI tool? Yes, it's like a BI tool, but there's a difference in emphasis. When I think about traditional BI, it tends to be analytical and tends to be sort of predictive, and it tends to be over a longer time frame. So a BI tool should look at, sales data and, number one, break down for me, which regions were selling the most widgets and which salespeople were selling the most widgets and what was my revenue by region, all of that stuff. Elasticsearch can do that portion. But then BI tools also frequently are predictive in that they say, okay, so if I add 3 more salespeople to this region, how should my sales change, right? Elasticsearch is much more real-time focused. With Elasticsearch, we're monitoring some set of infrastructure or hardware, and we're looking to find trends and patterns in the data as it's coming through in real time. So a lot of questions on sort of other technologies and how it compares. How does it compare to Memcache, to Splunk, to Hadoop? What I would say is, all right, well, let's start with Memcache. So, Memcache as a caching solution is essentially a storage solution. We don't think of Elasticsearch or search engines typically as storage solutions. It's really meant to be something that provides you the ability to stream in data, visualize that data, and react to what's going on in real time. Memcache is a little bit more permanent, a little bit more solid as a storage medium. When we think about Splunk, Splunk is really a full-blown application that has not only the ability to take in log data, but also to view that log data in a fully built-out way. Elasticsearch is more like a toolbox. It allows you to take in your data, but you'll have to build some visualizations. You'll have to put some work into it to get the information out of those. Of course, as a toolkit, it tends to be less expensive than Splunk, so there's a kind of breaking point where you say, okay, we're really getting the value from Splunk for this set of use cases, so we should use Splunk for that. And these use cases, we really don't have such a high need for the analysis that we want to do. We want to build something that's less costly and will give you essentially the same results, but you'll have to put a little bit more work into it. How is it different from Hadoop? Hadoop is a general framework for performing distributed calculation. Elasticsearch is a distributed framework, but it only performs search engine calculation. sorry, I'll take one last one, and then we will wrap up. How to find the health of index or shards. So I mentioned we do support a number of different CloudWatch metrics around your cluster. Most of those are, again, at a full cluster level. If you want to dig in to find out the health at an index or a shard level, we expose several APIs from Elasticsearch that allow you to do this. So in particular, we have an API _cat, C-A-T, that provides you information about indices. So you can do _cat/indices, _cat/shards to get information on those. In addition, there's a number of different stats APIs. So there's an _stats, which gives you overall index statistics. There's a nodes stats that gives you individual node statistics, including operating system, JVM, all sorts of low-level information that you can pull out of the Elasticsearch APIs. So I'm aware that we are running out of time. I want to thank you again for your time and attention, and look forward to having you try out the service.